Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to cover the definition of a mathematical sequence as a review for integral calculus. We'll give a couple examples listing out elements of a sequence and creating the formula for a sequence. Definition of a sequence, the mathematical definition, is that we have a function whose domain is a set of natural numbers. That would actually define a sequence of values. Now, this definition that I'm writing here is actually not permanent. It's somewhat fallible, but the most important piece is that it is a function. And that concept of it needing to have a domain of natural numbers is actually not totally true. Let me just give you a showcase what maybe a sequence could look like. A sequence of numbers. Let's just pretend we have 3 and 8 and 2, 1 and 1 and 2. And let's make a set out of that. So we'll make the set of possibilities. And I'll call this an example here so that we actually have this formalized as an example. This is a sequence of numbers. And we would often call that the first numbers, right? 3 would be the first number and 8 would be the second number in that set. And notice a couple things that are important here to note. First of all, numbers can repeat. Notice that the numbers in the list, like 2, number 2 repeats. That's perfectly fine. The number 1 actually repeats as well. Perfectly fine that numbers repeat in this list. It's still a function. It maps elements from the natural numbers into a set format. So let me go ahead and just show maybe in a list format that you would see in an algebra course, x versus y. In this case, y is actually going to be f of x. This is not technically the correct notation for a function, but I'm just showcasing this because it's a high-level review. I just want to kind of quickly go through. So when we input 1, we're talking about the first element here. We should get out to input 2. The second element should be 8. And I'm saying the word element. I will actually define that in a moment. The third element in our list is a 2. And the fourth element is 1, and so on and so forth down that list. Right? Now let's go ahead and talk about what I am actually saying here. I'm using the word element. So each member, let me pause this and actually write this down. So each member in our sequence is known as an element. And we can actually refer to an individual element in that list, as I have in this list, the sequence here. I have the first member and the second member. We can refer to those members as their index. So that's the first element, the second element. That first is the index number, the first, and the second is the second element, and so on and so forth. Let me write that down. I'll scroll down here. The position of an element in a sequence is referred to as its index. So the index for the number 3 is 1. The index for the number 8 is 2. The index for this specific number 2 is 3, and so on and so forth through this list. I should note that it does not necessarily need to be the case that our list actually starts with an index of 1. You can have a list, a sequence, that is, start with an index of -3 or +5. Then if you did that, you would have index number 5 and index number 6 and so on and so forth. Let me give you an example of that. And I'm slowly trading out our function notation from the previous example for what we will actually be using with sequences. So let's pretend as though this sequence we're about to build is indexed initially at a -2 and then increases by 1. In fact, it will be the case that that sequences, their indices or their indexes but it's indices. If you pluralize that, increase by unit amounts. So -2 is if we start with a -2, the next one in line will be a -1, and so on and so forth. And let's pretend that uh, -2, the index, leads to, let's say, 1 over root 2. And -1 leads to a -1 over root 2. And 0 leads to 3/2. And 1 leads to, I don't care, root 3 over 2, and so on and so forth, right? Dot, 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 all the way down the line. So you can see that in this case, I've chosen to, instead of start at the first element, I'm saying the first element is actually the -2nd element. It's kind of confusing when you do it that way. However, it is necessary to know that you can have sequences start with an index different than 1. Often it's greater than 1, but sometimes you can have them start with indices that are less than 1. I also want to mention that when we talk about elements or members of a given sequence, we do sometimes, and in fact in calculus, refer to those as terms. So I'm going to point an arrow at this and just call this also a term. I'll highlight that so that we have that kind of as an important statement. So I could, in our first example, ask you what is the third term of this sequence, and that would be 2. There's sort of a flaw, I think, with that language, because in mathematics, the word term is usually reserved for separate pieces of an arithmetic statement, right? It's pieces that are separated by summation or difference symbols. But still, you will find that there are some mathematicians that refer to these as a specific term, the third term in the sequence, and so on and so forth. But technically, they should be called elements. Finally, before we go into any more examples, it is important to note how we write down sequences in terms of notation. I already sort of hinted at it, but I would like an official statement here. Sequence notation, as a definition, varies actually depending upon if your sequence is a finite list or an infinite list. It doesn't really vary too much though. So what I'm going to do is use a subscript notation, so the first term in our sequence and second term and so on down the line. If it's a finite sequence, you would just go down to something like this, A1 through A sub n, right? And this is a finite sequence. That is a good sequence notation. Those A sub I elements would actually be traded out for whatever is in that sequence. So if the sequence was our original sequence up above, that A sub 1 would be traded out for a 3, A sub 2 would be traded out for 8, and so on down the line. But if you had an infinite sequence, generally we just write it this way, A1, A2, and now that the pattern is set, we use an ellipses to say that pattern continues. There's also another way you could write that. And in fact, most people will see it this way. They just see this A sub n. And that's kind of a weird notation. That requires some usual definition for what A sub n stands for. In mathematics, we will have a function that A sub n is defined by. And so given that function, we will often write the sequence notation in this brace like this with the function notation inside. I'll give you an example in a moment. Another way we could write this is, again, the brace, A sub I, well, maybe I'll use n, A sub n goes from 1 to infinity. This is a little more calculus-y, and that's what is nice about it. It kind of marries together our calculus notation and sequence notation. So different ways to write a sequence, an infinite sequence, and best thing to do now is actually see some examples so that we can really solidify this understanding. In this example, we're just going to go ahead and list out the first 5 terms of the given sequences that we have. Right now, I've only listed 1. In this notation, this just means the sequence is defined to be, or all elements in the sequence are defined to be given by that function, 4 times the quantity -2 to the nth power over n factorial. And it is assumed, if that is written without a subscript notation, or I'm sorry, without an index notation, it is assumed that this means from n equals 1 to infinity. That's the assumption that's made in the background. So if you see a sequence written like that, it is generally so assumed that it's going to go start at 1. So in this case, I'll just start writing out this terms of the sequence here. When n is equal to 1, you have 4 obviously times a negative 2 to the first over 1 factorial. When n is equal to 2, you have 4 times a negative 2 squared, and all the way down this list, right? And I'm not actually going to go to the fifth term because I just want to showcase the simplification here. Some people may not be familiar or may have lost their knowledge on factorials. So just to recall, n factorial is equal to n times n minus 1 times n minus 2. That product, or those factors, go all the way down to 2 and finish at 1. Therefore, 1 factorial would start at 1 and end at 1. So 1 factorial is literally just 1. So we have negative 8 over 1. 2 factorial, on the other hand, I'll just write it here, is 2 times 1, or 2. So that's going to be 4 times negative 2 squared is 16 divided by 2 is 8. 3 factorial is 3 times 2 times 1, which is 6. And the numerator of that 3 factorial there is going to be negative 2 cubed, which is a negative 8, times 4, which is a negative 32. And let's see, a negative 32 over 6 is a negative 16 over 3. The next one in line will have a negative 2 to the 4th, which is 16, and then times 4. And its denominator will actually be a 4 factorial. 4 factorial is 4 times 3 times 2 times 1. And you kind of get used to this. That's just going to be a 24. So let's see. The numerator, like I said, was, let's see, negative 2 to the 4th is 16 times 4 is 64 divided by 24. That reduces down. That's 8/3. You can double check my work if you want. And then 5, the fifth element of that sequence, will have a 5 factorial downstairs. You know how that's written. That's actually going to be just 120. I need to write that to mentally kind of hold that in my brain. But then the numerator is going to be 4 times negative 2, again, this time to the 5th. Negative 2 to the 5th is, I'm going to do my math over here, 4 times negative 2 to the 5th. Negative 2 to the 5th is negative 32. And we have a 120 downstairs. And if you simplify that down, it should be a negative 16 over 15. And this list will go on forever. Now, if somebody handed me that list, negative 8, positive 8, negative 16 thirds, positive 8 thirds, negative 16 fifteenths, and ... I may not be able to recreate this sequence definition right here, just because it's really difficult and challenging to actually recreate that. So just to know, if given a list, it might be very challenging to recreate the sequence based upon that list, or that list is based upon. So that's just a big heads up there. Another thing you can do with these examples is you can check out a list of the values using Desmos, for example. You could also use Excel or something like that. If you're going to use Desmos, you can go ahead and just add a table. And to create the table, you'll delete out that x sub 1. And in our first example, we had 4 times a negative 2 to the n over n factorial. I'm going to write this as 4 times a negative 2 raised to the x sub 1, technically, over x sub 1 factorial. Let's see if that actually works out. Yeah, it does. So 1 leads to negative 8. 2 leads to positive 8, 3, 4, 5, 6. It actually pre-fills these. Okay. So also you can see it gets kind of small there, doesn't it? Another thing you'll notice is off to the right-hand side. Let me put this in projector mode so you can see it and turn off the grid. it gives you a good little graph of these plots or these points, right? When n is equal to 1, the output's -8. When n is equal to 2, the output's +8. When n equals 3, it's, it just bounces back and forth. Kind of an interesting sequence because it's hovering near 0 in the long run, which should make sense because you're dividing by such a large number, but maybe not too much sense. In the second example, I just created this just to highlight a couple things. One, the notational difference between part A. Part A has that brace notation, and I had said some people use that notation. It explicitly defines the sequence, the function for the sequence, and then we plug in n equals 1, and we continue to climb from there. It's more often the case that somebody will hand you just a definition of the sequence itself. Our sequence, b sub n, is defined to always be cosine of n pi. If they leave it at that, you may assume that n starts at 1 and climbs up from there. It's a pretty safe assumption. So let's go ahead and do this. Just fill in the first, actually I don't need my brace that big. You can fill in the first few values here. The very first element is cosine of 1 pi. Second element is cosine of 2 pi. And you would continue that pattern down. Again, we wanted to do the first 5 elements of this list. I'm going to just write the ellipses there because we need to obviously simplify, and I happen to know that this will be a pattern. So that sequence is going to be, you can't leave it as cosines. This is calculus. You already know this, what these turn into. Cosine of pi is a -1. Cosine of 2 pi is 1. Cosine of 3 pi is a -1. So therefore, 1 and -1. Those are the first 5 elements, and I didn't bother writing the rest, obviously, but you know how the rest of the list goes. Those are the first 5 elements in this sequence. It's not a requirement right now, but it's worthwhile to mention. This is called an alternating sequence. It alternates between negative and positive values. Every element changes signs. So that is also true for the very first sequence I gave you, that the signs of its elements change, right? From negative to positive to negative to positive. That's an alternating sequence. And those are very important sequences that we will be dealing with in our course as we move forward. But let's go ahead and do one final example here. This example C is actually an incredibly important example because it has a uniqueness about it and ends up leading to some very theoretically important concepts, specifically something known as the Fibonacci sequence, which is a really neat sequence. But that's not what this is. But this style of sequence is very Fibonacci-esque. The reason why I say this is because if you note, they give us the very first value of the sequence. A sub 1 is defined to be 2. And then they say, well, from that point forward, the next sequence value in line is based upon the previous sequence value. That is known as a recursively defined sequence. When a sequence is defined in terms of its previous values, it's known as a recursively defined sequence. In fact, maybe I should just write that as a definition right here. Kind of making up this definition right now, but I think it's pretty good. Definition of recursively defined sequence. A sequence whose nth element is defined in terms of previous elements of the sequence is known as a recursively defined sequence. That is, I think, loosely pretty okay. Note that we actually have defined our sequence in this problem. I'll just write it, point and arrow at it. It is actually the n plus term, the n plus 1 term is defined in terms of previous elements, but that's okay. It still means it's recursively defined. It doesn't have to actually be defined in terms of the next door neighbor, right? You could technically have a sequence where the n plus first term is defined in terms of something that occurred quite some time ago, right? The problem with those types of sequences is you have to have a long list of initial conditions to eventually be able to start your sequence up. So you have to have, in this case, you have to have the n minus 7th and n minus 6th terms already found to be able to find the n plus first term. So that's kind of an annoyance. But anyhow, that definition aside, I'm going to erase these guys right here, get them out of my way. That definition aside, let's go ahead and fill out the first 5 terms of the sequence. Luckily, the first one's a freebie. The second term is going to be, again, now we're dealing with n equals 1 here. This n equals 1 in this formula being that we're looking at a sub 2. That's going to be a sub 1 over 1 plus a sub 1. So that'll be 2 over 3. And then a sub 3 is going to be a sub 2 over 1 plus a sub 2. You get the idea, right? So that's 2/3 over 1 plus 2/3, multiplying numerator and denominator by 3. You get a beautiful 2 over 5. It's actually a very beautiful sequence so far. I kind of like it. A sub 4 is a sub 3 over 1 plus a sub 3. Kind of writing quickly. Sorry about that. That's 2 over 5 divided by 1 plus 2 over 5. Multiplying numerator and denominator by 5. You get 2 over 7. And now you see this pattern. Notice a sub 1 was actually 2 over 1. A sub 2 is 2 over 3. Then 2 over 5. Then 2 over 7. You can guess the next one might be 2 over 9. Very curious if it'll end up being that way. You can actually prove that it is. Or that, well, you could do a proof showing what this will end up being in the long run. But let's just go ahead and do it this way. Multiply top and bottom by 7, you get 2 over 7 plus 2, which is 9. That's a beautiful sequence. 2, 2/3, 2/5, 2/7, 2/9. And you can kind of guess that there might be a better way to write this, although that wasn't part of the question. It might be neat to ask. So if you look at the denominator of a sub 1, you'll see it's the first odd number. The denominator of a sub 2 is a second odd number, then third, then fourth, then fifth odd number. And an odd number, generally speaking, can be written as either 2k plus 1 or 2k minus 1. And so if I want my first odd number to be 1, then subbing in 1 for k there gives me 2 minus 1 or 1. Second odd number, sub in 2, you get 2 times 2 minus 1, which is 3. Third odd number, 3 times 2 is 6 minus 1 is 5. You get the point. So there is actually a nicer way to write this recursive sequence. At least it looks like there is, where we could write a sub n is equal to 2 over, let's see, twice n minus 1. And that should technically be fine for this sequence. And you could prove that. That's not the point of this problem. In this example, we're asked to find a formula for the general term of the sequence. General term we usually just call a sub n. We will assume that this sequence defines a pattern. And also, we are going to assume that the sequence starts at an index of 1. And I think those are pretty fair assumptions. So let's go ahead and try to find a pattern here. One thing you should note, I'll go ahead and highlight that, is this is an alternating sequence. It goes from negative to positive to negative to positive. Once you see something like that, you should really think like there has to be a multiplication by a -1 occurring somewhere. So what you can do, and I'll write this in blue, is you can start by saying a sub n is equal to like a -1 to a power. Now, I'm assuming it's the nth power. I'm going to test that pattern right now. Remember, we're starting with n equals 1. So if n were equal to 1, the first element should be negative. If n were equal to 2, then -1 squared would give me a positive value. So that does seem to work out. So that's a very good way to kind of quickly check that your negative alternations there are set up properly. Now we look at how did we get from that first element to the second element to the third element? Is there some type of constant multiplication or addition happening there? In this case, if you assume it's addition, well, then you'd have to look at the difference between -3 and 2. You're adding 5. You're not adding 5 to get to the next one, though. So it's likely not the case that you're adding something over and over. By the way, it doesn't have to be addition or multiplication. It could be other things happening. But this is an initial example, so it seems as though it shouldn't be too terrible. It might be easier to see with later on with later elements to get from negative 4/3 to positive 8/9. Forget about the negativity. Just go from 4/3 to 8/9. It looks like I'm doubling up that power or that numerator, and I'm tripling that denominator. Well, let's see if that's the same case going from 8/9 to 16/27. Did I double the numerator? Yeah, it sure does look like it. Did I triple that denominator? Yeah, it sure does look like that too. Let's go ahead and look at it here. Did I double the numerator? Well, to get from 3 to 2, if I doubled that numerator, it would be a 6, and then that division by 3 would give me back to 2. So actually, yeah, that is true. Now, as a reminder, not all sequences are these products, right? They're not all developed by seeing a product happening every step of the way. However, this is one of those special kinds. They're that way, just introduction. So what I'm going to do is a very common tactic, which is to list out what that first element is. I know that when n equals 1, it's a negative 3. But then from that point forward, something magical happens. We have it listed, actually, let me highlight it, listed above right here, that 2/3. So every single time I take a step forward, it looks as though, and maybe it's not true, but it looks as though I'm multiplying by 2/3. Now, if I left it just like this, that would not be the case, right? If I let n equal 1, this is actually going to be a negative 2. That's a problem. So what I need to do is not allow this multiplication to occur when n is equal to 1. Luckily, if I set the exponent to 0 at n equals 1, that multiplication will just have a multiplication of 1. So 2/3 to the 1 minus 1 is 2/3 to the 0 or 1. And so when n is equal to 1, this will just be a negative 3. But when n is equal to 2, you can see that the exponent here would be a 1. And so we'd have 2/3 times 3, or 2, times the negative 1 squared, which is a positive 2. And now you could start testing this. Well, what about at this fourth element, for example? Let's see what happens. Negative 1 to the fourth times 3 times 2/3 to the 4 minus 1, which is actually just 3, right? Well, the negative 1 becomes positive. We have 3, and then let's see, I'll have times 8 over 27. And that'll be 8/9. And if you take a look, that's exactly what that fourth element is. So this looks to be the pattern right here. I'll box it up. Actually, I'll just highlight it. However, you could, and often will want to, simplify that statement. I personally like it the way it's written. Just cleaner for me to see what's going on. But some people will write this as a negative 1 to the nth power times 2 to the n minus 1 over 3 to the n minus 2. That's an alternative way of doing it. The 3's cancel, so you have 1 less power of 3 downstairs than you had before. Or another way is keep the 3 as a coefficient, but pull in that negative 1. Well, that's actually going to be kind of difficult in this case to do because that negative 1 actually does need to be there, now that I'm thinking about it. So we can't do that. But this is just an alternative way of writing it. I still probably would recommend writing it with a negative 1 to the n times 3 times 2/3 to the n minus 1. Personally, I just like that better. Not that big of a deal, but I think that's a nicer way of writing it. So.